Okay, so today we are going to start a new topic about which we have been talking quite a lot, but we actually have not seen the algorithms, etc. So it is the process scheduling or CPU scheduling. Right, so just a small recap that why is process scheduling required. So we are talking about multi-programming or time-sharing kind of systems, and CPU scheduling forms the central idea behind such systems. So the idea is that the CPU is very fast. It can do millions of instructions per second, even billions, and no one process needs so much computing resource. Therefore, better that you switch the CPU among different processes so that we ensure better utilization of the CPU. Okay. So we will mainly talk about process scheduling here. However, just to inform you that modern operating systems also have a lightweight version of processes which are called threads. We will discuss threads in the next topic, but just to understand that scheduling is carried out both for processes and threads. But the basic motivation for scheduling is to ensure better utilization of the CPU by switching the CPU from one process to another or from one thread to another. Now just continuing our recap for a couple of more minutes. Recall we have discussed about CPU burst and IO burst. So CPU burst for a process is that time when it is actually being executed on the CPU. And when it is waiting for say IO to be done, then it is called IO burst. So the typical expectation from a process is that it will alternate between CPU bursts and IO bursts. And we have discussed that when this happens, suppose a process is, so let's see this picture. So suppose this process is going through a CPU burst initially. Then it will maybe wait for some input from the user. So that's an IO burst. Again, it will do some processing with the data which was input, let's say. Again, maybe it will write to file. So it will wait for IO. So it's again an IO burst. Then again it will do some operations. That means it will be a CPU burst and so on. So typically this is how a process proceeds during a lifetime. It has alternate CPU bursts and IO bursts. Now the question that we are going to ask is, when a process goes from a CPU burst to an IO burst, then some other process must be allocated to the CPU. So how to decide that? Which process should be allocated next? That is the main topic of this lecture. So before that, just let me just ask maybe one question. Think of CPU bursts. Right? So many processes are having many CPU bursts. If you consider a distribution of the duration of a typical duration of a CPU burst, right? So many processes have different types of CPU bursts. Maybe some are long, some are short, etc. We want to plot a typical distribution of how long a CPU burst is. How do you think that distribution would be? I mean, I'm not asking for a mathematical function, etc. Just intuitively. If I want to plot a distribution of CPU burst times across many processes, across many systems, how do you think it would be, that distribution? Positively skewed Gaussian. Yeah, okay. I mean, well, as I said, I am not looking for a mathematical answer. So Shubham, you are not wrong, but I mean, I was just looking for some intuition. Okay, let me proceed. Typically, it would look like this, the picture here. So there would be a large number of short CPU bursts and a small number of large CPU bursts. Right, so mostly it will follow an exponential or hyper exponential distribution. So as you see, there is a big peak here. That means most of the CPU bursts are of this, say, 4 millisecond type, let's say, or 2 milliseconds. However, there are some CPU bursts which are a bit longer, but practically you see nothing beyond, say, 8 milliseconds. Right. So again, understand that 8 milliseconds CPU burst means a huge number of operations. Therefore, we are talking of that range, like few milliseconds. Maybe most processors are happy with just 2 milliseconds or 3 milliseconds. Some processors occasionally ask for say 6 or 8 milliseconds and so on. But usually it's a like exponential or hyper exponential distribution. Okay. So now this is the central question here of this lecture. That suppose the particular process was doing a CPU burst, now it has asked for some IO. Or maybe the timer has interrupted, etc. But whatever be the reason, the CPU has become free. Now, the next process which should run in the CPU should be selected. So how is it done there? How is that done? So if you remember this picture, we have seen this earlier, we had this ready queue. Right? So this ready queue contains those processes which are ready to be executed now. So that means they are not waiting for any IO or they are not waiting for any other event. So typically, one of the processes from this ready queue should be selected and allocated to CPU. And this is done by a program called scheduler. Okay. More specifically, sometimes the word short-term scheduler is used or CPU scheduler. Okay. So what does the short-term scheduler or CPU scheduler do? It selects which process should be executed next in the CPU. And we will talk about another kind of scheduler soon, but often the short-term scheduler is the only scheduler in the system. And this point is important. The short-term scheduler is invoked frequently, very frequently, like of the order of a few milliseconds. As I said, CPU bursts are of the order of say 2 milliseconds, 3 milliseconds, etc. So typically after every 2 milliseconds, this short-term scheduler will be invoked. That's why it has to be very fast. Like if you say that the scheduler takes 1 millisecond, that simply won't do. Because after every 2 milliseconds, you cannot waste 1 millisecond on scheduling. So this scheduler has to be very fast. Maybe it has to do its job in a few microseconds. So as I said, there is another type of scheduler in literature which is called long-term scheduler or job scheduler. The job of this scheduler is to select which processes should be brought into the ready queue. Okay. So the long-term scheduler decides which processes should be brought in the ready queue, and the short-term scheduler decides which process from the ready queue will be allocated to CPU. I hope the difference is clear. So the long-term scheduler is invoked much less frequently, maybe once every few seconds or even once every few minutes. And therefore it is okay if it is relatively slow. Okay. And the long-term scheduler, which decides how many processes are there in the ready queue, that means it basically controls the degree of multiprogramming. That means how many processes how many processes is the system at all considering at the same point of time. So I hope the difference between short-term scheduler and long-term scheduler is clear. Sometimes you will often hear about a medium-term scheduler also. However, all these things are written in books, etc. But often what is written here, sometimes the short-term scheduler is the only scheduler in the system practically. That means whatever process is submitted, it is kept in the system. So there is no, specific need for long-term scheduling. However, the short-term scheduler, of course, has to be there because someone needs to decide which process to allocate the CPU next. Okay. So in our discussion, we will mainly focus on the short-term scheduler, the one which will pick one process from the ready queue and allocate the CPU. That is what we will discuss about. Now one question is, when is the scheduler called? What is written in this slide should be clear from our previous discussions, maybe the discussions we had last week. So a scheduler is called whenever one process is, like one process will stop. will stop means will temporarily stop, and another process should be started. When can that happen? So case one is a process switches from running to waiting. So the process which was running, maybe it has done an IO call or a wait system call, which we have discussed. So that means this process no longer wants to run just now. It is waiting for some event, maybe an IO event or some child to terminate, and then it will run again. Therefore, its state switches from running to waiting, and the scheduler must be called to allocate the CPU to the next process. Similarly, a process can directly go from running to ready. That means this process did not want any operation. However, the timer interrupted or some other IO device interrupted. This process was not doing any IO, but some other process was doing IO and that IO device interrupted. So this process did not want to give up the CPU. However, the OS needs to do some work, like a timer is interrupted, etc. And therefore, this process will be taken from the running to the ready state, and the scheduler will be called to allocate the CPU to the next process. Okay. The fourth case, let me just discuss this fourth case first. The process terminates. Right? So the process, this is the last CPU burst. Maybe it was allocated a CPU burst of 2 milliseconds, but after 1 millisecond, the process ended. Right? So it called exit, let's say. So then again the CPU should be allocated to some other process. Okay. And now this third case, a process switches from waiting to ready. Okay. A process switches from waiting to ready. For example, it was waiting for the completion of an IO, or it was waiting for a child to terminate. Now that event has happened. Therefore, the process will switch from waiting to ready. Okay. Here also a scheduler may be called. Okay. May or may not, that depends on different operating system design. But why do you think a scheduler may be called here in this case? Of course, if you have any questions about the other three cases, then tell me. But I think the other three cases are easy to understand. We have discussed them. But this case, I would like you to say, why do you think this third case will require or may require a scheduler? Exactly, Sriharsh has a good answer. So, okay, what Shubham is saying is also correct, but the thing is that we have not discussed this part yet, but we will, maybe today itself or tomorrow, that sometimes processes may have priority, right? So assume that a higher priority process had called for an IO operation. So it was moved to the waiting state. And a lower priority process was allocated to CPU. Now that IO event completed. So now that higher priority process is no longer waiting, it is now again ready. And therefore, because it is of higher priority, it should be allocated the CPU right now. Okay. So in such situations, the scheduler may need to be called. Okay. So understand that this point is very careful. This point understand very carefully. just because a process has shifted from waiting to ready does not mean that it will immediately be allocated the CPU. This does not follow. Let me repeat, because this point is important. Suppose the process was waiting for some event. Maybe it had asked for an IO event, or it was waiting for a child to terminate, or simply it was sleeping, like it invoked a sleep call. So that event was completed. So now this process is no longer waiting. It is now ready. But that does not mean that immediately the process will be allocated the CPU. Okay. It can happen that there are many other processes in the system. Some other process will be allocated the CPU, etc., etc. But at some point, this process will also run. That is the purpose of bringing it back to the ready queue. The OS or the kernel should at least know that this process is no longer waiting, it is ready. But this does not mean that the kernel is bound to allocate the processor right now. So just to connect this, okay, this discussion, is this okay? This, what I said in the last 2 or 3 minutes, is this okay? If yes, then I have a question. If you have doubts, then ask me, otherwise I have a question. Can you see any connection of this discussion with a lab assignment that you are doing or have done? Maybe the assignment you are doing now, or any connection do you see? Okay, in the interest of time, let me say what I was just trying to point out. I think you are doing an assignment where you have been asked to make a process sleep and then wake it up, etc., etc. So as you do that assignment, keep a lookout. Suppose you make a process sleep for 2 seconds. Is it guaranteed that it will start running immediately after 2 seconds? Maybe not. Okay, so just keep this in mind. So a process may be waiting, and at some point it may become ready, because that event for which it was waiting completed. But just because this process has become ready may not mean that it will immediately be allocated the CPU. That depends on the scheduler. Okay, so just keep this in mind. Maybe you will see a better connection when you do this assignment, etc. Okay, let me move on. So I hope this part is clear, that there are these different processes, there are these different situations under which a scheduler will need to be called. Now, I would again ask, I have again another question. Can you group these, let's say, so there are 4 cases here. Okay. So this case 1 and case 2. Do you see any fundamental difference between these 2 cases? Case 1 and case 2. Think from the perspective of the process which was running. Do you see any fundamental difference between these 2?
Sir?
Yes?
Sir, in the second scheduling, in the second point, how means if an IO interrupt happens, then a process will go from ready to waiting, or no, running to waiting, or running to ready.
Hear me?
Yes, sir.
So the
But
rule
I have a doubt actually.
fine, but the rule we follow is if you have a doubt, you should write in the chat.
Okay, sir.
Suddenly start speaking. This is the rule we have been following throughout the semester. Please write in the chat. Okay, now coming back to the question that I asked. Yeah, okay. First of all, so Dhruvi, what you are saying is not quite correct. In the first case, there has not been any interrupt. The process has simply gone for IO. Right, so there is no question about interrupt in the first case at all. Right. So yeah, you might say that is one difference. That in the second case there was a timer interrupt or an IO interrupt, but the first case there is no interrupt at all. But apart from that, any other difference do you see? Okay, Shobnath has a good answer. Yes. In case 2, theoretically, this process itself may again be allocated the CPU. Though it is very unlikely that the same process will be given 2 CPU bursts, but let's say theoretically it is possible. Okay. Yeah, so Pankaj also said the same thing, that in the first case, the process cannot run at this point. It is waiting for some event. But in the second case, it is theoretically possible that the next time slice also is given to this process and it runs. Right. However, but there is another difference which I wanted to point out. I'll tell that, but let me see Shaumitra's question first. Shaumitra is asking, how can an IO interrupt make a process to go from running to ready state? Will not only running to waiting will happen. Okay. So this IO, so I guess Shaumitra you are asking about this case. This IO interrupt is not due to this process. Maybe some other process has asked for an IO operation. That IO operation has completed. Therefore, that IO device interrupted the kernel. So the IO device interrupted, and therefore the kernel is running. This IO interrupt is not due to something which this process has done. So this process which was running right now, this IO interrupt is not due to any action taken by that process. This was most possibly some other process had asked for some IO earlier. That IO operation completed, and therefore the IO device interrupted. And if IO device has raised an interrupt, the kernel should address that interrupt. We have discussed these things. And the interrupt service routine should be run, etc. Therefore, it can happen that this process is kept on hold. It is moved to the ready state, and then the kernel handles that interrupt, and then again calls the scheduler to decide which next process will run. Shobitra, is your question, have you got your answer?
Yes, sir.
Okay, right, thanks.
But sir.
Yes.
Sir, but that is not that similar to the waiting to ready state? If IO interrupt completed for a process, so it is similar to the waiting to ready.
Okay, let's explain once more. Suppose we are talking about, so suppose there are 2 processes in the system, A and B. At a certain point, A was running. Okay, B was ready. A is running, B is ready. A calls for an IO. So A will be shifted from running to waiting state, and the IO operation will begin. Right? So A has called for an IO operation. The OS. So the moment A calls for an IO operation, control will go to the kernel, because A has asked for an IO operation, which can happen only with the kernel's help. So A will be put from running to waiting. Okay. The IO operation will start, the scheduler will run, and let's say it allocates B, the CPU. So now A is waiting, B is running. Now let's say that this is this case. A went from running to waiting. Okay. And the scheduler ran, and the scheduler allocated CPU to B. So now B is running, A is waiting. Now at some point, while B was running, the IO operation that was requested by A completed. So that IO device now raised an interrupt. Okay. Now when an interrupt has been raised, the kernel needs to service that interrupt. Right. So because this interrupt has been raised, now B, which is running, will be moved from running to ready. This is the second case. So the IO interrupt came because some IO operation requested by A completed. But now B was running. But B will be moved from running to ready state because the IO operation requested by A completed. So B will be moved from running to ready, and A, which was till now in waiting, will be moved to ready. This is the third case. Because A was waiting, A had requested for an IO operation, it completed. So A is no longer waiting. A is moved to ready. So now A and B both are ready. Now the scheduler will decide to whom to allocate the next CPU cycle. Is this clear? So Shobhitra, you can unmute yourself now. And
yes, sir.
Yeah. So anyone else having doubt in the example that I described using the two processes A and B? Okay, if not, fine. So then let me go back to the question I had asked, that is there any difference between this case and this case from the perspective of the process? And I see that Rahul has given the right answer, which I wrote. So in this first case, the process itself did something which made it, go from running to waiting. That means it voluntarily gave up control of the CPU, you may say, because it requested an IO operation on wait call. But in the second case, this process did not do anything. This process did not voluntarily give up the CPU. Rather, some other event happened, due to which the CPU was taken away from this process. So from the perspective of the process, the first case is kind of voluntarily giving up the CPU. And the second case is involuntary, as in the CPU was taken away from it. So I hope the distinction is clear. And this leads to this important distinction of the two types of scheduling: non-preemptive scheduling and preemptive scheduling. Non-preemptive scheduling is this, that scheduling happens only when a process voluntarily gives up CPU. That means scheduling happens only when a process switches from running to waiting or when a process terminates. These are the two cases when the process voluntarily gives up CPU. And in case of non-preemptive scheduling, once CPU is allocated to a process, it keeps the CPU for as long as the process requires. Contrast with this, preemptive scheduling. In preemptive scheduling, the CPU can be forcibly taken away from a running process. For example, due to timer interrupt upon completion of time slice, etc. Okay, so going back to slides, now you see this case and this case, this case, the case 1 and case 4, these fall under non-preemptive scheduling. So here the CPU voluntarily gives, the process voluntarily gives up the CPU. But this case comes under preemptive scheduling. Also this case, somewhat, comes under preemptive scheduling. That means the process did not want to give up the CPU right now, but the CPU was forcibly taken away from the process. Okay. Now there are a few issues associated with preemptive scheduling, which we would discuss later in the course. It may result in something called waste condition, which is an undesirable condition, etc. We will discuss this later. But just to know that sometimes some core kernel routines are non-preemptive. That means the core kernel routines are the ones which, let's say, are very important for smooth functioning of the system as a whole. Maybe the scheduler itself. So, like those processes are non-preemptive. That means these kernel routines are so important that it is guaranteed that the CPU will never be taken away from those processes forcibly. They are allowed to retain the CPU as long as they want. But yes, usually such core kernel routines are very quick. That means a few microseconds or, and they will be done. So no one usually takes away the CPU from them because they are of the kernel itself. Okay, so I hope the distinction between preemptive and non-preemptive scheduling is clear. Okay, now just to note another term which we have also discussed but not in detail. So suppose at some point the scheduler is run and it selects the process which should be run next. Then what happens? Another kernel module called dispatcher comes into play. So the dispatcher actually gives control of the CPU to that process which has been selected by the short-term scheduler to run next. So the dispatcher is the one which switches context, and we have discussed what does switching context mean. All the register values, etc., which are saved of this process should be loaded to the CPU, etc. And then it should switch back the CPU to user mode, and then it should jump to the proper location in the user program to restart that program. This is what is done by the dispatcher. How do you think dispatcher will know the proper location in the user program to restart that program? How do you think the dispatcher will know the proper location in the next program? Yeah, right, sure. So this information has been stored in the PCB of that process. Right, yeah. So I think from your knowledge of COA, you know that there is a register called program counter, etc. So when this process was earlier saved, right? So when this process was earlier switched off, earlier moved away from the CPU, at that point its PCB had been saved, and the PCB contains these entries, like what was the program counter. So as you know, program counter contains the address of the next instruction to be executed. So now when the dispatcher will load back that process into the CPU, the program counter value will also be loaded back, and therefore the CPU will know which instruction to be executed next. And that instruction to be executed next will be of that next program. Okay. So this is how the dispatcher will work. So first the scheduler will select which process to run next, and then the dispatcher will allocate the CPU to that process. And then again, the CPU switches to user mode. Now the kernel will no longer run, rather the next process which has been scheduled will be run. Okay. And of course, as you understand, both scheduling and dispatching, latency should be low, because ultimately these are overheads. scheduling, dispatching, these are all overheads. Actually we think that when a user process is running, that is the actual work is getting done. Whereas these things like dispatching, scheduling, these are kind of overhead. Therefore, we would like scheduling, dispatching to happen very fast. Okay. Fine. So now the main question remains. So we have discussed when the scheduler runs, etc. The different situations on which a scheduler should run. Now the main question to handle is how to schedule. That means once the scheduler is running, it sees several processes in the ready queue. How will it select which process to run next? Okay. So that is what we will discuss now. So at this point, any questions? Okay, if not, let me proceed. So there's a next deck of slides. Let me open up. Yeah. So can you see these slides? Okay, fine. Okay, so yeah. So we have discussed this non-preemptive and preemptive scheduling, right? And now let us discuss. So first of all, let us actually discuss the scheduling. So first, let me ask that. So scheduling, just like say, okay, I think all of you have done. I'm sure all of you have done algorithms, PDS course, etc. So you know there are different sorting algorithms, right? So. Okay, Shomitra has a question. Any scheduling will be a preemptive or non-preemptive alone, or it will be the mixture of both if we want preemptive? Usually a scheduling algorithm is either preemptive or non-preemptive. But if you want a hybrid, whether you can design, that I am not very sure. Maybe you can. But usually, by definition, a scheduling algorithm is either preemptive or non-preemptive. Okay. There may be a mixture, say, though we have not discussed the details, we will, but since you have asked the question, I can think of a mixture or a hybrid scheme where, say, some very high priority kernel processes are not preempted, but other user processes can be preempted. Right, so in that case, you might think of a hybrid scheme, right, which is sometimes preemptive, sometimes non-preemptive. That means for certain high priority processes it is non-preemptive, but for certain low priority processes it may be preemptive. So you can think of a hybrid scheme, but in general, by definition, a scheduling algorithm is either preemptive or non-preemptive. Okay, here another question. If I do only preemptive, then how to proceed when a process terminates? Okay. See, a scheduling algorithm is preemptive. That does not mean that it absolutely needs the process to stop, otherwise it cannot run. Okay. So if the currently running process has terminated, then definitely, whatever be the scheduling algorithm be, preemptive or non-preemptive, then definitely the scheduling algorithm will run. Okay. So again, preemptive means that if I say a scheduling algorithm is preemptive, that means that if a process is running now, it still can snatch the CPU from that process. The scheduling algorithm has that power to preempt a process. That means it has the power to deallocate the CPU from a running process. This does not mean that unless any, the scheduler cannot do its work if no process is running. Okay, so if a process has terminated, definitely any preemptive or non-preemptive algorithm, whatever be the scheduling algorithm, it will be used. Okay. Okay, Pankaj is asking, like we discussed in the initial lectures, isn't non-preemptive risky? Some malicious or badly programmed process might take CPU forever. Yes, that risk is there, and that is why most modern operating systems use preemption, use preemptive scheduling. And maybe some processes are non-preemptive, but those are very trusted processes. As I said, some core kernel routines. So that's the OS itself. If you say the OS has turned malicious, then it's a very difficult proposition. But otherwise, as I said, all modern OS use preemptive scheduling. Some special, very internal kernel routines, which are very trusted, are sometimes given non-preemptive access to CPU. Okay. But otherwise, in general, it's preemptive. And yes, what Pankaj said, that's one reason why it is so. Like usually, the preemptive is the more preferred choice. Okay. Any other questions? Okay, let me proceed. So, as I was telling, we will, in this lecture, today and tomorrow, we will discuss several scheduling algorithms. Right? So the situation is like, all of you have done sorting in basic PDS or algorithms course. So there are many sorting algorithms. So whenever the program has many algorithms, it should tell you something. What is that? So like, why is there not a single scheduling algorithm which everyone uses? Similar question, why is there not a single sorting algorithm which everyone uses? So whenever there are several algorithms, what does that tell you? Exactly, trade-offs. Right. So possibly there are many different, Yeah, exactly. So what Dhrumin said and Mukul also said, that usually there are different metrics, all of which may be desirable in some different situation. And different algorithms may be better for optimizing different metrics. Right. So maybe in sorting, like there are different kinds of desirable things, like efficiency is one, so number of comparisons should be small. Also maybe stability of sort, that's another desirable metric. Now some algorithm may be very efficient, but it is not stable. Whereas some other algorithm may not be so efficient, but it ensures stable sorting, and so on. So whenever there are different algorithms for a particular problem, usually the intuition is that there will be multiple metrics, and different algorithms are better for optimizing different metrics. Exactly the same is the case in scheduling. So first let us understand what are the different metrics, and then we will see the different algorithms. So these are all different metrics which have to be kept in mind, or which should be kept in mind when designing scheduling algorithms. Let's understand the metrics. First is CPU utilization. Of course, this is the very basic thing. To keep the CPU as busy as possible. Okay. So, that is the whole idea of doing this multi-programming, etc. So, definitely a scheduling algorithm should be such that it should keep the CPU as busy as possible. Then comes something called throughput. Throughput is the number of processes that complete their execution per time unit on average. So let's say, per time unit maybe say per minute or per second. Maybe second is too small, say per minute. So on average, how many processes are completing their execution per time unit? say how many processes are completing their execution per minute. This gives a very global picture, but still it gives a picture about how efficiently processes are getting completed. Okay. So this is a global criteria kind of, that the number of processes that complete their execution per time unit. Ideally, we like this to be large. Now, a few metrics from the perspective of a particular process. So these two are global metrics, like not from the perspective of a particular process, but system-wide metrics, you might say. Now the next few are process-specific metrics. Let's understand them. Turnaround time. So turnaround time is the amount of time to completely execute a process. That means the interval from the time of submission of a process to the time of its completion. This is the total time that a process takes. Now this whole time may not be CPU time. Maybe some time would be spent executing on the CPU. Some time will be spent waiting for I/O. Some time will be spent waiting for a child to terminate, and so on. But even with all these, the turnaround time is the total amount of time it requires to completely execute a process. A bit different is response time. Response time is the amount of time from when a process is submitted to the time when the first response is produced. Okay. So this is not the time. So in case, what is the difference between turnaround time and response time? The calculation of both starts from the point of time when the process is submitted. But turnaround time will complete the whole, turnaround time will be computed when the execution of the process is fully over. But in case of response time, the response time will be computed when the first response is produced. Typically, response time is practically more important for an interactive system. Like, think about it. Suppose you are running a program and you want some inputs. After that, there will be a processing phase and then some output will be produced. So, how quickly is the input at least taken? So this is our mindset, as in, at least if the input is taken, then we are satisfied that the program is running. After that, maybe we are okay in waiting for some time, because we know that we have given a complicated input, maybe it will take some time to process the input, that's okay. But as long as the first response is not received, we will be impatient. Is the program at all running, etc. Think about it, like, again, I am giving a very high-level example, nothing to do with operating systems per se, but just to understand why fast response is important. Think of a time when you have started to download some big file. As long as the download does not start, we are impatient. Once the download has started, and a progress bar is showing, 2% done, 5% done, etc. Usually we are okay, as in even if we have to wait for 5 minutes, we understand that we have asked it to download a big movie or a big video. So maybe it will take 5 minutes, okay. But as long as the first response is not received, we are impatient. That is the human nature. Therefore, for interactive systems, more important than turnaround time is the response time. That means how quickly at least the first response is produced. And next is now even then, for turnaround time and response time, as I said, especially for turnaround time, not all this time is under the control of a scheduler. By that I mean, suppose a process has large turnaround time. Is it because the scheduler was bad? Maybe not. Maybe that process waited for a lot of time for I/O. Therefore, its turnaround time was high. It is possible. So rather, what is specifically used to understand how good a scheduler is waiting time. So the amount of time a process spends waiting in the ready queue. Okay. So this is specifically the time during which the process was not waiting for an event, but it was made to wait because some other process was running. Remember, You could note carefully the time that the process spends in the ready queue. Okay. So this is the exact time which is under the control of the scheduler. So the scheduler made that process wait for so much. So when we discuss the algorithms, you will see that we give most weightage to waiting time, because that is the time which is actually controllable by the scheduler. Okay. Okay, and the last thing is burst time. So the amount of time a process is executed on the CPU. So typically if we see, we will see such algorithms, but sometimes a scheduler may prefer processes with a small burst time. Because, so why do you think so? So I said that suppose there are some processors with large burst time, CPU burst time, and there are some processors with small CPU burst time. I made a statement that sometimes a scheduler may prefer or may prioritize processors with low burst time. Why do you think this can happen? Exactly what Shubham has said. So suppose there are three processes, one has huge burst time, the other two have small burst times. Now if the process with huge burst time is scheduled, then other two processes will have to wait for a long time. Instead, if the scheduler first schedules the two processes with small CPU burst time, then those two would be completed quickly, and then this process with a large burst time can be scheduled. Right, so less people have to wait. The processes have to wait for less amount of time. So all these criteria are taken care while scheduling, and that is why there are different scheduling algorithms, because some algorithm may be better in one respect, while some other algorithm may be better in some other respect, and so on. Okay. So, but as we will see, when we start discussing these scheduling algorithms from tomorrow, we will focus mostly on the waiting time, because that is exactly the one which is under the control of the scheduler. The turnaround time may not be under the control of the scheduler fully, because it depends on how much time the process spent in waiting for IO. But the waiting time is specifically under the control of the scheduler. So we will focus mostly on waiting time. However, we wanted to tell you this slide because you should understand that there are these different scheduling criteria, and therefore there are different scheduling algorithms. Okay, I see a question from Samitra. Are the last four metrics irredundant? What is irredundant? Okay. Or are they correlated to some extent? If there is correlation, what is the extent of correlation among those? Okay, I'm not fully sure of this question, but of course there is some correlation. Like if the waiting time is large, of course the turnaround time will be large. Okay. Then the waiting time may actually depend on the burst time. This will be clear when we discuss the algorithms. Because the example that I just said, there is actually an algorithm which says that schedule those processes first which have low CPU burst time. So then if a process has high burst time, its waiting time will be large. So of course there is correlation, but I am not sure of, Shamitra, I am not sure of your first question, that is, why should they be redundant or irredundant? This I am not sure. Of course they are correlated. One thing should be pretty clear even now, that turnaround time will depend on waiting time. Right, so of course they are correlated. Plus, as you will see, sometimes the waiting time will also depend on burst time. That depends on the specific algorithm being used for scheduling, etc. Okay, that's a good question. Are all these algorithms heuristic based? Kind of, yes. There are a couple of theoretical guarantees, but yes, those theoretical guarantees take a lot of assumptions which are often not true in a practical system. Therefore, yeah, you might say that for practical purposes, these algorithms are heuristic based. Okay. But yeah, there are a couple of algorithms which try to have some guarantees. Okay, Shomitra, yes, unmute yourself.
Sir, there are correlation you said. So we want to, if in a case we want to minimize the waiting time, so turnaround time will also be minimized. So why they are the different scheduling criteria? Means, so if we want to focus on one thing, then the rest burst time is fixed for a process, but the different processes will be accordingly means scheduled.
Let me understand your question. You are asking why is it not to only focus on waiting time?
No. Why we are focusing on waiting time, but why are they for different scheduling criteria? They are correlated. So if we minimize the waiting time, then turnaround time average per process will also be reduced. So
I'm not sure of any guarantee like that. Like, can you mathematically prove that if waiting time is reduced, turnaround time of all processes will reduce? I am not aware of any such guarantees. That depends on things about regarding how the processes are, how many IO processes you have, how many CPU bound processes you have, etc.
But sir, the CPU burst time will not be fixed for a process.
So
sir, turnaround time will be the total waiting time plus means I don't know exactly means it will be the CPU burst time and the waiting time and the IO burst time. All these will be there, right?
turnaround is a summation of all those. But
yes, sir.
In that suppose there is a particular algorithm. Suppose you have two algorithms and you are trying to decide between two schedules. Algorithm A gives lower weighting for some cases. It does not scheduling. It may not be. In some other cases, the turnaround time of processes may be smaller due to B. These things can happen. Therefore, what I am trying to say is, we will focus on waiting time because that is the time which is specifically under the control of the scheduler. However, I am not aware of any such guarantees that scheduler which gives lowest waiting times will be the best because it is guaranteed to lead to less turnaround time, etc., etc. Those things depend on what kind of processes are there, whether you have more of IO bound processes or more of CPU bound processes, etc. Okay, last question for today by Mukul. That's an excellent question. Do schedulers learn, as in do their policies update over time? Okay, that's an excellent question. The scheduling algorithms that we will discuss do not learn over time. They are just basic heuristic based, algorithms which have some heuristics. Like say, one heuristic can be that have some priority of the processes and then decide, or have some this simple heuristic that if you know this, if you can figure out the CPU burst time of a process, then first schedule those processes which have low burst time. So basically the algorithms that we will discuss are meant for those. These fixed kind of heuristic based algorithms. But yes, there is sufficient scope of making a scheduling algorithm learn something. That means suppose an intelligent scheduling algorithm which learns what would be a good way of scheduling processes on this system. Right. So if some of you have done courses on like machine learning, reinforcement learning, etc. Sure. Intelligent schedulers are possible to design. We won't discuss this here, but yeah, those can be thought of. And maybe some research is going on in that direction. I'm not fully aware, but as of now, the algorithms that we will discuss or which are commonly used, they are heuristic based. But of course, I mean, since Mukul has asked the question, let me just conclude by saying this, that two aspects are of research interest. One is how to design intelligent schedulers, which will themselves learn how to schedule well. For that, one may use things like, like machine learning, reinforcement learning, etc. The other thing is fairness. Right? Again, I'm not sure if we will discuss here, but there is a question of being fair towards processors. Like no process should be starved, or etc. etc. So how to design a fair scheduler is also of interest. In fact, Linux, there is a lot of discussion about a fair scheduler which Linux apparently uses. I'm not sure if it's used in all distributions, etc. But yeah, Linux is said to use a fair scheduler and so on. In the basic lectures, we are not going into those, but let's see. Let me talk with Professor Mainak Mandal also. Whether we can give some flavor of those, we'll see. Right. But initially, we will discuss some simple heuristic-based scheduling criteria. Scheduling algorithms. Fine then. Okay, that's a good question. Okay, let's end this class today. We will continue tomorrow. Thank you.